Boom. Yep, I'm bad about that. Okay, so you can either just write answers on a piece of paper. I will share out the pictures of the scoring guide to these questions later on. And then, or you could make a copy of the Google Doc that you can edit yourself. So start, but let's everybody write what you think the ground state electron configuration for the Fe2+ ion is. And again, sometimes it's easier to write the full thing and then take off electrons.
Miss Baskin.
Yes, dear.
When you get to the it goes like once you get to where there's a D, it goes D then P, right?
Yes, but you should not need to go to P after the D here.
Yeah. I just didn't know if I had to like jump over and then jump back.
Yeah, no.
Okay.
All right, we good on this?
I think so.
Okay, so I'm a little confused.
Yeah.
So we did this thing last class where we started with the noble gas that was closest to it.
If you want to do that, yep.
But if we do that, then where do we start from after we have the noble gas?
You would look at the period number where your element is, and that would be your next number, and you always start with an S after a noble gas. So what period is iron in?
Period goes
Left to right.
left to right. Okay, great. 1, 2, 3, 4.
It's the rows rather.
Yeah, so it's the fourth row down. So you would start with then 4S.
Okay.
Because I was like, this whole thing goes left to right, but yeah, it's the rows.
Ms. Baskin, is the noble gas or is it like any element, like the element?
It has to be the noble gas if you're going to write it that way.
Oh.
And when I show you the scoring guide, what you'll see is they don't care which way you use. So that up there is the electron configuration for iron, right? And then you could write that as argon 4s2 3d6. So that would be regular iron, but they're asking for the iron 2+ ion. So 2+ means what are you doing with electrons? Adding or taking away?
Taking away.
Taking away. So we got to take away 2.
3D.
Which 2 are you going to take away?
It's from the 3d6.
Well, I mean, would it be the S2? But why though? That doesn't make sense. Why wouldn't it take it from the outermost?
You always take them from the highest energy level.
Oh.
All right, you take them out of the highest number.
Like the one that's closest to, wait, what? Oh.
Right, the 4 is the biggest number.
So, okay, that was my other question.
Oh.
So you drop, when you get to D, you drop back 1. Like the number. So they don't consider this, they consider the row with FE as the third period.
No, it's the 4th period.
But it's just on it. It just third.
But where D is, because D is always sitting in an energy level number below.
Okay.
Yeah. So here's how you're going to remember this. Valence electrons, how many valence electrons can you have?
8.
8. And which sublevels, which letters are those valence electrons coming from?
D. What? What
Your
letter?
options are S, P, D, and F. Which of those gives you the valence electrons?
S?
S and
P.
P. S and P. And only S and P.
Why? Wait.
All right. Valence electrons are only coming out of S and P, which means that you're only gaining or losing electrons into S and P, never D.
Well, that I think that makes sense because it's like, well, at least visually on the periodic table, S and P are the only ones on like the outside. Like that's the way I see it.
Visually, yeah.
Yeah.
So when you ask why is that the case? Because S and P are always going to be a number above D, right? So we've sitting here, we've got 4S2. If I filled up 3D10, right, the next thing I would write would be 4P. Whoops. 4. Damn it. 4P6, right? And so again, 4 is higher than this 3 in between. D is never a part of a valence electron. So your valence electrons are always going to come from S and P. So if you ever forget which electrons do I lose when I make an ion, it's always going to be S. It's always going to come from S and P.
Okay.
Now, the question doesn't ask for it, but so let me write here. So the correct answer here, 1s2, 2s2, 2p6, 3s2, 3p6, 3d6.
Okay.
Or you could write argon 3d6.
So for 3 plus, will we take away 4s2 and then make it 2p? No, make it 3s1?
No. So if you lose another electron, where do you think that next electron is going to come from?
The next.
The next highest energy.
It wouldn't be. You wouldn't have argon, would you?
You'd still have argon. It would lose that. Now you'd start losing D electrons.
Okay.
So once, right, because that's the weird thing about the transition metals. They lose those S electrons first, but the reason that it could be iron 2 plus or 3 plus is because it's got the access to D electrons.
Okay. So when you do it with the noble gas, noble gas format, you don't have to put like the charge. Well, they don't have charge. Never mind. I lied.
Yeah, no, you literally just write the symbol in there.
Okay.
Okay. So next it says the radii of the ions are given in the table, right? So using principles of atomic structure, explain why the radius of Fe2 plus is larger than Fe3 plus.
Oh my gosh, I know this one.
Okay, so I want you to write down what you think. Now you could write a one-sentence answer to this. This is
I need
not
you-
a paragraph type thing.
I need you to explain how to make it.
Because you heard Sean over there writing a novel.
Yeah, if you heard me, just the pen, just
Scratch it. So, well, if somebody thinks they have either a decent answer or a kernel of an idea that they want to share.
Me.
All right, Taylor.
Okay.
Oh, Taylor.
Thank you for the support. Isn't it because you have to take an electron away to make from Fe2 plus to make Fe3 plus?
It is related to the difference in electrons, yes.
And then isn't it like, no, that's all I got. Never mind. That's it.
So
No.
who has more electrons?
Fe3.
Fe2.
Fe2, sorry.
No.
Okay.
Okay.
Fe2 plus has more electrons.
Oh, because it takes 2 away as opposed to taking 3 away.
Yes, ma'am.
Nice.
But it okay, you're right.
Where I'm kind of confused though is that they both only lost 1 whole energy level. They
So
both still have 3D,
Right.
like something.
True.
Say something.
but isn't it?
My answer?
Carl?
Yeah. I said that because Fe3 plus has less electrons, this allows the nucleus to pull harder on the remaining ones, which decreases the radius.
That is almost all the way there. You
Mm.
also have to talk about what the electrons are doing to each other.
Oh, repulse. Thank you. So wait, the full answer is Carl. You want to hit that?
Oh, you're funny. All right.
You don't.
So wait, is it like so? Just for me, right? It's because Fe2 plus has a greater number of electrons than Fe3 plus. So the electrons are repel more, pushing each other outwards to increase the radius, and there's a less attraction to the nucleus, which also causes a greater radius.
Well, here they technically have the same amount of attraction in because they have the same number of protons.
Okay, so you have to talk about the electrons and the.
So here you have to talk about repulsion.
Okay.
So, Miss Baskin.
Yes.
Never mind. You gonna write it down, then I'll ask a question.
That's literally it.
Fe2
There's one more electron.
Okay. But like, well, I guess they usually only ask these like comparing ions of the same element. So like, but basically, whenever we see a question like this, we just talk about the repulsion of the electrons.
So so there's 2 possible ways that they can ask about this. So they can ask about transition metals that can make a 2 plus and a 3 plus, right? Because those are pretty much the only ones. In which case, you want to talk about electron repulsion. The other thing they can do is ask about things that have the same number of electrons. So say, for instance, neon, which has 10 electrons, and fluorine ion, or F minus, which also has 10 electrons, and ask about those sizes. So if you're talking about the same element with different charges, talk about electrons. If you're talking about different elements and comparing their sizes, talk about the attraction to the nucleus. Does that make sense?
So you would say,
because in this instance on the paper, these have the same number of protons, which means the attraction is the same, and therefore it's due to repulsion. If you are talking about, for instance, say, neon, which has 10 electrons, F minus, which has 10 electrons, and oxygen 2-, which also has 10 electrons. Those all have the same electrons. So in theory, they have the same repulsion, so therefore talk about attraction.
Okay, so you would say like something neon has
Right?
more protons
Uh-huh.
than the other two, causing more attraction, causing it to be smaller.
Yes.
Okay.
Yep.
Okay, I understand. That makes sense.
Okay. All right, so now let's talk about then C, which is talking about the difference between the Fe3+ and the Fe2+ attracting to water. And if it says justify your answer using Coulomb's law, that means in Coulomb's law, you only have two options because there's only two factors involved in Coulomb's law. Distance and amount of charge. That's the thing to remember there. So here, it's asking you to basically decide which of those factors is the bigger issue in terms of attracting water.
Ms. Baskin, what does that word say? You have distance and then something.
Amount of charge.
Wow.
That says a month.
Shut up.
Ms. Baskin.
Yes,
Cassidy said her wing keeps knocking out the Wi-Fi, and she tried to tell you, but her remind's not even working, so she asked me to tell you.
okay. That's cool. Thank you. Hopefully she can get a good enough connection later to watch the video.
Yeah, hopefully.
How is wind? Oh, okay, never mind.
So Ms. Baskin, I just read that it said that for Coulomb's law, that like charges repel and unlike charges attract, which is just opposite attract and stuff like that.
Uh-huh.
So is it like, nope, let me stop. I'm gonna go back on mute and think about it. Marinate on it.
Yeah, get into it.
Let it simmer.
So you can answer this question correctly using either aspect of Coulomb's law. You just have to say it in a sentence. So if you wanted to talk about distance, what would the correct answer be here that explains why Fe3+ has a stronger attraction to water than Fe2+? What would that answer be?
Since the radius is smaller, that allows the nucleus to kind of like pull harder on the water molecule.
Yes. That is the answer based on distance, right? Fe3+ is a smaller ion than Fe2+, so it has a greater attraction for the water.
So for the amount of charge, would you say because Fe, wait a second. Because Fe3+, right?
Mm-hmm.
Isn't Fe3+ less negative?
Well, you would just say it's more positive.
Well, more positive, right?
Mm-hmm.
And so that gives it greater attraction to the
Yes.
But do you have to like reference which side of the thing?
No.
Okay. Cause I was like, cause I know the hydrogen side versus the oxygen side is different, like the dipole or whatever.
True.
Get vocabulary. Dipole.
Oh
I'm
yeah,
having a dipole moment.
I'm having a dipole.
Yeah.
Yeah. Literally, people will come walking up to be like, "Are you having a dipole day?" And she's like, "We'll get us together." I'm like,
Yep.
The world's having a dipole moment.
Yeah, right?
honestly,
World.
I'm in the dipole house. Okay.
dipole.
Now, Sean, you did bring up a possible way that they could extend this question, meaning they could then have a box and say, okay, so draw how water molecules would be oriented around an Fe3+ ion.
Yeah.
I hate that.
Okay, so that's a unit 2 topic, but like that's a way that they could extend to that. So that's kind of where we need to really think, because they're gonna try and test 7 units in 2 questions, which means they're gonna end up smashing things together. So I think that you are more likely to see questions like B and C here, because that's not something that's easily Googleable. Making comparisons between 2 things is a very, very likely way that a question like this could be asked. Now, I would also say that since in the years past, they have largely focused on doing things like having 2 different ions of the same element, I do think it is likely that we might see something more like this, where we're looking at, what's called an isoelectronic series, where they could give you ionic rate, distance data there, and then ask you to base a comparison, because it's asking for the same skill, but in a different way than they've done it in the last couple of years. So.
And Ms. Baskin, you said, when was the date where they're gonna release questions that are supposed to be more like this?
They're saying is mid-April. There's a group of AP teachers who are coming up with some practice questions. They are like AP, they're College Board question writers already. So they were like, well, if we had to come up with this, here's how we're doing. So I'll take a look at what they're coming up with next week.
I decided to move.
Okay, great.
Okay. So it's this first question that I did want to spend the most time on, because I do think it's most likely, if we see, however we see Unit 1 incorporated on this test, I do think it's most likely to be up here. But I will say, both of the last 2 years, there have been free response questions based on photoelectron spectroscopy. So this is the one from 2 years ago. And you can see that, again, if they give you one of these diagrams, the first question is always, what the hell is this thing? So figure out, what is this thing?
Periodic table.
And you just got to remember what that first peak always represents and go from there.
Wait, okay, but before it went left to right, and now it's right to left.
No, it's still left to right. Don't worry about the numbers down here.
Okay.
Just remember that the electron configuration is always starting on the left.
But Ms. Baskin,
Yes.
like a little extra. So like the reason the binding energy is stronger at the beginning is because it's closer to the nucleus, right? It's like harder to take them off.
Yes.
Okay.
Is that zirconium?
Girl, what? No.
Is it nitrogen?
Nitrogen?
Nitrogen.
Yes, Sean.
Saffron.
Come on, is what, girl? Where did you find that?
Let's
Wait,
not.
okay. So it's nitrogen.
Oh.
All right. This first peak represents 1s2. You will also notice that they've drawn these, they've given you a diagram that's got the lines on it. So it represents, you know, each one of these lines essentially represents one electron. So 1s2, the next peak has to be 2s2. This would be 2p, and the lines indicate that it's 1, 2, 3. So 2 plus 2 plus 3 is atomic number 7. So that's how you know it's nitrogen.
Nice. I was close. This is good.
You were close?
Period. Yes.
I was just still counting, and you were like nitrogen. I was like, okay.
Yes. Sorry, we jumped the
Caleb,
gun.
me too. I was close.
Girl, you said zirconium. Shut up.
Where is zirconium? I don't even. How did you get
Where did you get down there?
40. It's element number 40.
I was about to say it's
ZR?
element 40. She saw this 40 and was like, zirconium? Okay. Now, this was a question that kind of frustrated people when it came out 2 years ago because parts B and C kind of seem really forced to put with this question. But this is kinetics actually shoved into the end of a photoelectron spectroscopy question. So this is going to kind of be how our questions are though, right? They're going to have to jam together different topics all into one thing. So you need to not find it so jarring. You just need to recognize when you've switched topics and look at your equation sheet for something to jog your memory. So it says a radioactive isotope of the element decays within a half-life of 10 minutes. And then it asks for the rate constant K, including your units. So on your equation sheet, scan and see if you can find something that says half-life.
Found it
Where?
at the bottom next to kinetics.
I see.
Okay, so what does that equation give you? What is the thing that says half-life?
I think it's a T. It says T,
Time.
and then
Uh-huh.
Oh, this
How does
thing.
K equals rate constant? Oh wow.
Okay, so and it's labeled all those things, right? So it's labeled that this is half-life
Yeah.
and
so
that
nice.
this is rate constant, right? So they tell you those things.
0.693.
And then the 0.693.
Where'd that come
So
from?
what
Oh,
is
never mind. I see it. Never mind. Sorry.
what is B asking you for then?
The rate con.
Okay.
Oh, so wait, you already got two of the things.
Yep.
Oh, so they was really playing with the girls. They was trying to get them tripped up.
Wait, where's the 693?
Because they give you the 10.
It's, the 0.693 is part of the formula.
They just give you 10. That's it. That's literally it.
Oh,
That's all you need.
And they said solve. That's literally it.
So
They do some
algebra says, how do you rearrange that equation?
You multiply both sides by K.
Yes.
You undo
What's
it.
right there? Wow.
And then to get K by itself?
You divide that by the half-life. So
There
it should be
you
0.693 divided by half-life.
Okay. So what am I plugging in my denominator?
10.
Okay.
Wouldn't it be just 10 as the whole, right? Yeah.
Yeah. So then the answer there is super easy. You don't even need a calculator.
Move the decimal.
Move the decimal, 0.0693. And it says include the units. Is there a unit in the top?
No, because it's a rate constant.
Well, there are units with rate constants,
Oh,
but
you're
is
right.
there a unit with this top number?
No.
No. So what's the unit with the bottom number?
Time.
And what specific time?
Minute.
Minutes.
Minutes. So what's my unit?
Minutes.
Minutes?
K per minute? Is there
K
something
per minute.
Why would they do that?
Ew.
Oh, 1 minus. Oh, I hate the 1 minus so
Why?
much.
So it's 1 over minutes? Because it's
Right. You can write it as 1 over minutes. That's the same thing.
But why is
That's
it
my
that?
point.
Because
That's
minutes in
cool.
my denominator, so it's got to stay in the
Yeah,
denominator.
for the rest of my days.
Right. Now, when we go over the kinetics unit, since you get to use your own formula sheet, we are going to add lots of annotation to that kinetics box
Lots of it.
about units
Lovely.
and labeling each one of those formulas so that you know what to use. Because I would say that the biggest thing about the kinetics unit that we used to get tripped up on was actually missing points for units. So we're going to fix that. All right, and then C is technically also kinetics, but this is just a logic problem. So it says of 64 atoms of the isotope originally present, what is the expected amount of time that will pass until only one atom remains? So I have 64 at time 0. After 10 minutes, how many do I have?
Half of that,
Which is?
32.
I add another 10 minutes. After 20 minutes, how much do I have?
16.
16.
Oh, we're doing up a half because it's half.
Yep. Add another 10 minutes. After 30, I have.
8.
Add another 10. After 40, I have.
4.
4.
All right.
Oh my
Add
gosh.
another 10.
2.
After,
1.
and then,
1.
so how much time was required?
An
0.
hour.
60 minutes.
60
hour.
minutes. Or 1 hour.
0.
So wait, is this system that you just did, is that eligible for our show how you arrived at the answer?
Absolutely.
Wonderful.
Because I don't want them to be like, what is this
Yeah.
system that they've come up with?
Because the other way to do it would be to use that natural log equation thing. And I'm like, no. When you're talking half-life problems, you can do a logic method and it's actually much simpler.
But Miss Basket,
Yes, ma'am.
if I were to see this problem, I wouldn't know what to do. So I
Yes,
know
you
that's a little
would.
crazy.
You
I
would
know
know what to do.
No, I wouldn't. But like, I thank you for believing in me. So I should look like for this specific problem to tell me that I need to half it until I get 1. Like, how do I approach?
The only way that the only piece of information that you have here is half-life. So you know that you have to use that. But, and like I said, when we go over kinetics, the thing I will remind you is that half-life information for us is only going to apply for first order reactions. And
Okay.
so again, the other way to approach it is to use the half order equation, which we're going to do a good job of labeling on your formula sheet that this is what we're looking for, right? That this is a first order thing. So here, plugging in, it would be the natural log of 64, because that's the thing at time t, minus the natural log of 1 because, or sorry, I did that backwards. All right, because time t, they want to know how long does it take to get to 1. We start with 64, and then we have negative 0.06693 times t. So in your calculator, you could do natural log of 1, right? ln of 1 minus ln of 64. ln of 1 minus ln of 64. Get a number that would be negative 4.159 equals negative 0.60693 times t. So divide both sides by that.
And you'll get like 60.
And if I did it right, you get 60, right?
That just seems like.
So either method works, but most people can logically do the method in black on the right and make less mistakes than you would trying to deal with the natural logs and putting them in the right way and everything.
That, in the words of Miss Jackson, that sounds like a waste of my minutes doing that natural law. That was a waste of the minutes.
Okay, so we're going to switch to the last question. And here's another PES.
But why
Don't shout it out this time.
What is that? Why it look like that?
You sound good.
Why is it built like? Why does it have these things?
Those are still just the binding energies, right? They're still just giving them to you, but
Oh,
it doesn't matter how they present it to you. You always read it the exact same way.
Mm-hmm.
So let Kayla count. Don't shout out the answer.
I won't do it. I won't shout it out. I promise. I do have a question though, Miss Baskin.
Yes.
If it like goes past an energy level, you have to assume that it's full, right?
What?
So, like, I know that it's a 2p6.
Yeah.
Okay.
You're just going all the way down. I did it. I'm not gonna say the answer, but I know that. Okay, wait, Miss Baskin. So the what is it called? The exponents, or are they? I guess.
Yes, those are exponents.
Those are equal. Like if I add them all up, they're equal to the number of
Yes.
Protons and electrons.
Yes.
So I need to find an element that has that number.
Yes.
Wait a second.
Lovely.
Can I count? No, I can't count. I messed up.
Yeah, I got it.
Is it?
Yes.
Hold on, girl. Don't do it.
It's on the screen.
I didn't say it though.
I figured it out.
This is great. I like
This I almost felt real dumb because I just looked in the wrong place, but I got myself together. I got it together.
So, Miss Baskin, isn't the number okay? Isn't the no? It's the atomic number. I said what number it was on the periodic table sheet. That's what I did, right?
I don't know. What did you do?
Did
you get that answer?
Because the atomic number and the number that it is on the periodic table sheet are not the same thing.
No, they should be the same thing.
They are.
What
did you put? The top number versus the bottom number?
No, you know what I did last time? I took a number off of the
off the axis. Yeah.
Yes. So no, I got it this time. I did. Okay.
So but yes, maybe for like a question like this.
Yeah.
How many points will we find here? Because like I know I made a really dumb mistake, but like if I were what happened was I was able to write the electron configuration, but I ended up just like looking too fast, and I accidentally wrote magnesium instead of calcium. So like, how many points would I like? Do you think this will have?
So each part here would be a point. So if we were taking the regular test, these end questions, and this is a question 5. So questions 4, 5, 6, and 7 are each worth 4 points.
Okay.
So you can see here that A part 1 would be worth a point. A part 2 would be worth a point, and B must be worth 2 points. So if you got part 1, if you wrote the electron configuration but then wrote the wrong element, like you'd miss that point.
Okay, yeah.
Okay.
But I fixed it. I got myself together.
Okay, well that's good. And then this last question kind of threw people because they weren't expecting it.
Oh wait.
That's on our wow.
So, and they weren't expecting it because it has been so long since a question like this has been asked. People were like, oh, wait, what? So this is calculate the wavelength in meters of radiation needed to remove an electron from the valence shell of an atom of this element. So first off, which of these numbers, and now it makes a little bit more sense why they wrote the numbers the way they did. Which of these numbers down at the bottom represents a valence?
4s2.
Yeah.
The thing in the 4s2. So it's this. That is an energy. So if you look on your formula sheet,
Yes.
How do we get frequency?
okay, so we have this formula, right? And what is the question asking for?
A wavelength.
Wavelength. And wavelength is this guy.
Your V's look great. I mean,
They're not V's, they're nudes.
listen, but you know what I meant.
I like them.
Okay.
They're cute.
So what is not on your sheet is those two equations combined. But if you get to annotate your sheet, we'll then annotate your sheet.
Yes, Lord.
So
I'll put that
let's
right
see
now.
here. Nu is C over lambda. Hey, what's new? C over lambda.
Over lambda.
Right. Okay. It's a really bad joke, but it works.
Please be quiet.
At least it's new.
No, but did you hear Sean's laugh?
Why did I just get it? I just got it.
Okay. So this is the combined form of the equation. So you can annotate your formula sheet with that. And the nice thing here is 2 of those 4 things are constants. And
I
they
have a
gave you
question.
1.
Constant. H is a constant, and
H is a constant.
Oh, that's Planck.
C is not a constant, is it?
C is a
Planck.
constant.
Oh, yay! And then we have E, which is the 0.980 times 10 to the negative 18. And
Yep.
then we're looking for, what's it called? The upside down Y.
The lambda.
Upside down Y, yeah.
Sure.
No, that number is seriously small.
So this is more a an exercise in making sure you can enter things in the calculator, because everything has scientific notation.
Mm-hmm.
So, and what did we say our E was?
They said, "Are you smart, honey, or are you dumb?"
Oh. I do have a question.
Yes.
No, I don't. I lied.
Cool.
I
Sometimes
thought.
it needs to happen. Sometimes you need to tell a lie.
Well, it wasn't a lie. It was just I
Well, you lied. It's okay. You lied. You
Oh.
lied.
misspoke. Calling me a liar out of my name.
Well, you called yourself a liar.
Oh, you're a
Out of
truther.
me.
Exactly what you just called yourself. So thank you.
I think we should focus on lambda.
I think you should not be a liar so much.
Oh,
I love that this is on YouTube. Like,
I know.
yeah.
Oh,
We are in the recording.
But my face is not
Y'all
showing.
just made
No,
fun
I-
of yourselves.
This
Oh, wait.
headshot, I can't.
Wait.
Every time this headshot shows up.
Isn't it a good one?
Yes, cute. Friend.
it is.
Don't be a hater.
No.
Jessica's she's gonna be teaching future classes. It's gonna be like, I have some videos on YouTube from last year's class. Actually, you might not wanna. They might not be useful.
Oh no, it's
This
useful.
is very useful. Excuse me.
Because
Okay.
we're asking all the
So,
necessary questions.
How many sig figs?
Well,
Read.
they gave us 3.
Oh, they gave us 3.
They did.
Oh, from the
Bam.
Right, you right.
Okay. So what are we getting for an answer with 3 sig figs?
I didn't even pick up my calculator yet. Wow.
2.03
2.03. And what's my exponent?
times 10 to the negative 7th.
And what is my unit?
Wavelength is in
Meters.
Meters. That's it.
Mm.
So here they basically gave you 1 point for plugging things into the equation and 1 point for the answer.
Period.
That's a terrible question. I should get like 15 points. That's
So wait, but this is considered this is still under atomic structure. So this is all technically 1 unit.
Yeah.
You're gospel.
Now, here's the thing. Do I think they're going to ask you to use this set of equations this year? No, I don't. But
Just in case.
New.
Yeah. Yeah. So,
What do you infer that they're gonna ask us more about?
so I think it is much more likely that they are going to tie together this sort of concept that we saw in B and C with something around bonding or Lewis structures or something like that.
Right.
So because you can relate attraction and Coulomb's law, those kinds of things, with structures or attractions between molecules or atoms or things like that. So I think that's most likely how they're going to incorporate this atomic information from Unit 1.
That makes sense. Thank you.
Mm-hmm.
Watch us get on this test and it's gonna be like, calculate the molar mass of hydrogen. That's it.
And
That was
you
fun.
get a 5, and you get a 5. No.
Oh my gosh, yeah.
Okay.
Okay.
There should be a chemistry show. Wait, wasn't Bill not? Never mind.
You're not a science guy.
Bill.
Oh, Lord.
Did any of you actually watch the show? I just want
No.
to hear.
Yeah.
I only watched it in science class.
Yeah, same.
Really?
Okay, so this is the specific scoring guide. I'm going to put this in the weekly plan so that you can look and see how they've used the language and everything here. But the only other things for today is a reminder to add stuff to here, and it doesn't have to be text. You can drop in pictures, you can drop in whatever you want, but let's get some information in here. And then so get your contributions onto the collaborative notes by Monday, and then you need to do the personal progress checks. So
Oh yes, that was my question. How many do we have to do for this one?
just do them.
So do all of them, like all
Yeah.
6? Okay.
Well, yeah, well, do Unit 1.
Do Unit 1. Okay,
Yeah,
gotcha.
Unit 1, because that's what we just reviewed, multiple
Yeah.
choice, and the let me know if there are problems doing the free response personal progress checks, because I think since they changed some settings on some of the free response questions, some of them might be glitchy. So let me know that, but that's all you need to do. Personal progress checks, drop some stuff in here, and then we'll do Unit 2 next week, which is bonding. We're going to go back and look at Lewis dot diagrams and Vesper and talk about tetrahedral and all that stuff.
Oh, thank you,
No.
boy.
But at least we can have our notes this time. We can have our notes this time.
Honestly, with
So
those
it's like-
shapes,
Yes,
that was the death of me because I just never took the time to actually learn them.
right.
So all those questions, it'd be like, what is a tetrahedral? I'd be like,
So, and I will tell you the other thing next week is since they're giving people the option of typing answers up or writing it and taking a picture, there's no way you're going to be asked to draw a structure.
yeah.
You are going to be asked to interpret.
Yeah.
So that's a different frame of mind.
First,
Okay, so that's a different thing for us to focus on review-wise.
So they'd be like, what shape is this?
Yeah, like
is
I
she
mean,
bent? No. Is she bent?
Oh,
well, how many ways are there to get bent?
2.
Two ways to get bent.
I don't know how.